We use a concept called as demand paging with virtual memory. Demand paging. Okay, let me write it here. So what is virtual memory? Only a part of the process is going to be present in the main memory, which means only few pages are going to be present in the main memory at any time. Now, which pages are going to be those few pages? That is the main question. So here the problem is we don't know what the future is, isn't it? We don't know what the process might require in future. So what we do is we are never going to load the page until it is required. That is called demand paging, which means don't load any page. Loading means into the main memory. Don't load any page until required. So if it is not required, we'll never load it, right? That is called as demand paging. Now what is the problem with this? The problem is whenever any page is referred for the first time, the chances are that that page will not be present in the main memory, and later maybe for the second reference, third reference, it might be available or might not be, but that is okay. But for the first time it will not be available, right? That is called as page fault. Page fault means we are trying to refer to a page which is not present in the memory, right? So what happens is, see, CPU is going to generate this one logical address, and then logical address is going to contain page number and page offset, isn't it? Now if I take this page number and if I get into the page table, now page table contains this frame number and one more bit. Oh, I told you that in the earlier case there is a bit called as valid invalid bit, which is going to say whether the process is present in the whether the page is present in the main memory or not. Please correct it. It is not valid invalid. I told you in the previous one, it is not valid invalid. It is present or absent bit. Actual bit is present or absent. Valid invalid bit has a different meaning. Valid invalid bit says that whether the address generated is valid or not. Sometimes what happens is, even though your virtual address space is 32 bits, which means CPU is generating 32-bit address, the process might not have a size of 2 power 32, right? That is a different case. Okay, so instead of valid invalid bit, you please make it as present or absent bit. Now using the page number, if I get into the page table, then the present or absent bit is going to say whether the page is present or not. In case if the page is present, yes, we can get into the main memory, and then we can get into that particular frame and we can get the particular word, right? If this page is present in the main memory, if this particular page is present in the main memory. But then what happens if it is not present? So if valid invalid bit says, if present or absent bit says that it is not present, it is absent, right? Then this scenario is called as page fault. Page fault. Okay, don't get confused. The earlier concept where TLB was stored in the page table, page table was stored in TLB, and when the page table entry is not present in TLB, that scenario was called as TLB miss, right? And here it is called as page miss, or it is also called as page fault. Page fault means the page which you wanted is not present in the main memory. Then what is the problem with this? Then if the page is not present, then the time is going to be increased in order to get the page into the main memory. What are the actions that happens here is, so whenever the hardware generates a trap, hardware generating a trap means the page which you are actually trying to refer is not present in the main memory, then that will lead to hardware trap, which will lead to interrupt. Then the operating system will be woken up. Now operating system will take control, and then there will be a context switching. A user process is running. Now user process has to stop and the operating system will start running. Operating system is also a process, right? And therefore there has to be a context switch. Now operating system, what it will do is, it will find out what is the page which was trying to create the trap, and then it will try to go to the main that secondary disk, hard disk, and then it will try to read the page. So operating system will initiate the read request, and once the page becomes available in the main memory, again operating system will schedule the process where it has stopped. Let us say instruction I of some process has generated the trap, which means it tried to access a page which is not present in the main memory. Then what happens? Then exactly at that instruction I, this particular process will be stopped, and operating system will take over. That is where there is a context switch, and now operating system will get the required page into the main memory, and once the required page is available in main memory, again it will schedule the process with again instruction I. Then what happens? Again now instruction I will behave as if it has never happened before, right? Which means it will again get back the context of the process in such a way that process acts as if nothing has happened, and again it will restart the instruction I, and now at this point the page will be present in the memory and it will be accessed, right? But anyway, there has to be a context switch. Let us say, see, if everything is fine, which means if the page is already present in the main memory, then the time taken will be around nanoseconds, just the memory access time, right? Main memory access time. Now in case, let us say this memory access time is in nanoseconds, alright? Now in case of page fault, what happens is there has to be a context switch. So for the context switch, what is context switch? Now the process which is doing this page fault has to call the operating system, right? Now operating system has to run, therefore there has to be a context switch. Now for this context switch, the time taken will be in microseconds. Microseconds means 1000 times this one. Why is this so? Is we have to execute some few instructions in the operating system code which might take microseconds, right? And now after the operating system has start running, then operating system will place the request for memory reading from secondary disk into the main memory, right? And for that movement, let us say for the copying, what is that we are trying to copy? A page from hard disk to the main memory, right? For that copying, the time taken is going to be milliseconds, right? And then again there has to be a context switch from operating system to the user process, right? So all these activities, right? So again there will be interrupt, and then interrupt service routine, everything will be there. I'll talk about interrupts later anyway, okay? So now anyway, it is a lot of time consuming activity, isn't it? So if there is no page fault, then the process is actually going to run very fast and smooth. Now if there is a page fault, process is going to take a lot of time, right? Now what happens if there are lots of page faults? What happens if every reference is a page fault, right? Then the effective memory access time will become effective memory access time to access the secondary disk, right? So if there are lots of page faults, then the time taken to execute the program is going to increase because of the lot of paging activity, which means we are going to move a page from secondary disk to the main one, and then the other way, right? So that is called as trashing. So trashing is when there are lots of page faults, or in fact if number of page faults is equal to number of memory references, which means almost for every reference of the memory, let us say page fault is 50%, which means out of every 2 references one reference is going to create a page fault. If that is the case, then most of the time is spent just reading the page from the hard disk into the main memory, right? Then this particular scenario, it is called as trashing. Now what we should do in order to eliminate this trashing is come up with better algorithms, right, which will be able to guess what is the requirement in the future. But it is impossible, right? See, if we know the future, we always take the better decisions. It is never possible. We wish we could, but then it is never possible, right? Then come up with the better algorithms in such a way that which will closely approximate the best algorithm available. Okay, what I mean to say is okay, see this. Now let us say there are various things here. So let us say a process has got only 4 frames allocated to this, even though the main memory contains many frames. In order to keep the degree of multi-programming high, what we try to do is we try to assign some fixed number of frames, or it is done, or some assignment is going to happen. There are various algorithms which are going to assign. Anyway, what happens is when the page numbers P1, P2, P3, P4 are already present in the frames, and now if I want the page number 5, then one of them has to be replaced with the new page, right? That is called as page replacement. For that we have algorithms. If you could do some better kind of page replacement algorithms, then maybe we could reduce the page fault rate. It is very important that we reduce the page fault rate, because the more the page fault is, the more the time required for memory access, and the slower the process execution is going to be, right? So how slower is it going to be? Now watch it. Now the effective memory access time in case of page fault is, if there is a page fault, let us say page fault rate is P, right? Then the effective memory access time is going to be P into service time. So service time is, or it is also called as page fault time, service time or page fault time. So this is the time taken in order to get a page and again restart the process in case of a page fault. In case there is no page fault, right? If there is no page fault, you have to directly get it from the main memory, right? Then it will be just memory access time. So this is the effective memory access time in the light of page fault. So actually what happens is, if there is a page fault, then I have to do a lot of work, and which will be very high compared to the memory access time. Yes, in fact, after doing all this work, again I have to fetch the instruction or whatever the word is from the main memory. Therefore, I have to again add page fault time plus main memory access. Okay, are you following it? I'm not sure. Let me just take the example and explain you. What I mean to say is like this. Assume that there is a process. And now the process has got many pages, right? And assume that there is main memory. Then with the concept of demand paging, what happens is, we'll start the process even without loading any page in the main memory, right? Then CPU, whenever it generates the logical address, right, it will contain two things. One is page number and other is page offset. So whenever it generates the first address, it will find out that this page number is not present in the main memory. How will it find out? Through the page table, right? In the page table, present or absent bit is going to specify it. Then what happens is, the required page, it has to be loaded into the main memory, right? And then again the same instruction will start, which will generate the same logical address. For this entire time, to stop the process and then copy the page from the secondary memory to the main memory and again start the process. This is called as page fault time or service time. Now this is going to be very high compared to directly accessing the main memory, right? So in case if there is a page fault, then the effective access time is going to be the page fault time, the page fault rate into page fault time. In case if there is no page fault, then it is going to be simply MA. But in any way, even after loading the required page, again you are supposed to read the concerned word from that page. Therefore, I am even supposed to add MA even in the case of service time. But then we need not add MA, because generally the page service time will be very high and the page memory access time will be very low. In this sense, it will be in milliseconds and it will be in nanoseconds, which means it will be 1/1,000,000th of the part. So if this is 1,000,000 seconds, 1,000,000 milliseconds, then it will be 1 millisecond, something like this. If it is if it is in 1 millisecond, in milliseconds, it will be in nanoseconds. Therefore, we generally don't worry about adding this factor, right? So now this is going to be even more complex when we combine the concept of TLB with the page fault. Now first thing is, whenever we try to refer to a page entry, then that page entry, the page table entry, might not be present in the TLB, that is called as TLB miss. And next, whenever you try to refer to the concerned page, the page might not be present in the main memory, that is called as page fault. Now there is some probability of this TLB miss and TLB hit, and some probability of this page fault rate and page fault hit and page fault miss. Now these two concepts can be combined and we can solve the questions. Let's see that.